chairman. So it's Nicolas Brunel from Evry, and we'll talk about aligning curve.
Okay.
Well, thank you.
Okay, thanks for the introduction. So I'm also half a speaker. Okay, so I will present you an ongoing work about the use of a Frenet Serret framework for analyzing data in FDA, functional data analysis. So this work started with my co-author Juhyun from Lancaster University. Was about really FDA. So we wanted to do FDA, and then we discovered the Frenet Serret frameworks and classical apparatus in geometry, and that we found it very interesting and useful for analyzing curves and doing usual stuff in FDA. So I will give some slight motivation at the beginning, explain, if needed really, what is the Frenet Serret framework and what we think it can provide for analysis. And then we will give how we can use it for aligning curves in FDA objectives. So our very first consideration was that FDA is very good and very interesting for analyzing 1D curve, because in a way it's very easy, because you just have to reconstruct your curve by non-parametric ways, typically by doing basis expansion or local polynomial. And then there is some kind of straightforward way of dealing with the variability. And typically, it comes from the fact that when you have 1D curve, basically you can deal in an obvious way for the phase variations, which is x-axis variation, and the y-axis variation. And with that, you can analyze, doing statistical analysis and doing alignment, FPCA, functional regression, because it's very clear. You have, in a way, no question to what is a good way of representing your data. But when you go to multidimensional functions, then the basic thought that you could have about, okay, I have to find what is my phase amplitude variation. You have so many ways. And if you take this simple bunch of curves, so you see that, okay, you have something common, but it's not really easy to say, okay, I varies around something. And so it seems that it really likes geometric variations, but how can you represent this geometry? So probably we are all here for discussing about geometry. So maybe it can be obvious, but you need to define clearly what you want to do. And we had also another problem when dealing with this kind of data, is that if you want to do that, and so when you have noisy data, I mean discretely observed and with noise data, what you have to do, you have to reconstruct your curve first. And so you can do it by non-parametric stuff, non-parametric tools, and usually what you can do, you do some kind of basis expansion, so you use B-splines or sines or maybe wavelets. And what you do it component-wise, so that you have a big basis. You tensorize your basis, and then, okay, because you deal with a kind of 1D object, you say, okay, no, I want to use sparsity, and then I will do L1, L2, just to reduce the dimension, because in a way you just have a curve in a big space, but you just have a curve. And we were not really interested in using all this kind of sparsity penalties or machinery. And we wanted to, okay, maybe use this kind of geometric constraints in the representation of our data. So it was really the beginning with the use of the Frenet Serret. And another motivation for doing that is that usually in FDA we already talk about the geometry of curves. So I just recall some very basic problems that you can do in FDA. What we do is usually percussion analysis when we have two curves, x0 and x1, and we just want to have a kind of match. So we just look for translation or the rotation just to have them close. And the other big problem just for representing the data and dealing with the data is to do the registration problem and to find a good diffeomorphism in order to align the curve x1 and x0 and to find the good h. So it was another big motivation that if we want to deal with multidimensional curve, and typically with 3D curves, we should look at a convenient geometric way of representing the curve. And that's why Frenet Serret became obvious. So I will recall some very basic stuff of geometry. And that, okay, we just consider very nice curves, which are regular. So you can differentiate them 3 times. The first derivative never vanish. And okay, what's important is that your derivatives are linearly independent. So you introduce the arc length parameterization. And so we just need to say, okay, so with a dot, we have the differentiation with respect to time. And we'll use okay, the prime here in order to deal with differentiation with respect to arc length. Okay, so ST, capital T, L, is the length, total length of the curve. And we'll deal essentially with a curve, capital X, indexed by the arc length. Okay, and so we assume that we can do pre-processing, very simple, that we estimate the derivative, we estimate the arc length, and reparameterize all the curve just by considering this arc length parameterization. Okay, so okay, no problem. So I think that it's not really interesting just to introduce a notation that we want to find good function in the space of increasing diffeomorphism. Okay, okay, standard problem. So we want this kind of function in that space. And what we want to do is to, okay, when we will do the alignment, we will, okay, we want to align this function. So S0 and S1 are the arc length abscissa, and H, okay, just to reset the notation. So an interesting feature that we have seen when you do this very basic Taylor expansion, in fact, okay, in a way it's really obvious. It's like a tautology, but when you do your basis expansion, and it's what we use for doing the reconstruction of the curve, we say that okay, our small change is that what happened at point S plus H is what happened at X plus this. And what's interesting is that, and the big interpretation of Frenet Serret is to say that X prime, and the third derivative is just a basis for your 3D space to represent the direction of move. And then finally, what does only the Frenet Serret? It says, okay, you take these derivatives and you compute and you do the orthonormalization. You take T, you normalize, you differentiate T, and you get the normal, and you just need to complete to have a complete frame. And so you got a matrix which is a rotation matrix, and which is very easy to compute from these derivatives. So okay, so not so easy, of course, but it will be my conclusion. So let's go forward again. What's really interesting is that with T and N and B, so a solution, in fact, the Frenet Serret is solution of the Frenet Serret ODE, which kind of complete description of the data and self-content. And what happens is all the geometry is contained in this equation. So you have kappa, which is a curvature, and tau, which is a torsion of your curve. So okay, very simple description of your TNB, and from the TNB you can get your function. And another way still of telling the story about ODE, or about the Frenet Serret ODE and formula, is to say that in fact you have your Frenet Serret, so your moving frame moves into FO3, and is solution of ODE, and you have A, which is an antisymmetric function, which is in the Lie algebra. So in fact, to any curve, a 3D curve, but obviously for a multidimensional curve, you can associate a trajectory in a SOP, and which is controlled by a very simple matrix coming from the Lie algebra. And so it was really the thing. Okay, it's nice because we have a compact way of representing the data. So in a way, we just have to say that we deal with solution of a particular differential equation, and we just, in a way, just have to compute the kappa on tau. Obviously, it's a big problem, but again, I will talk about this problem later on. And okay, and we call the solution for a given theta. So theta is a generalized curvature, meaning the curvature, the torsion on the standard curvature, and it gives a Frenet path. Okay, and the Frenet path contains all the informations on the curves. Now it's here just only to afraid us. It's just standard ways of introducing curvature and torsion is to say, okay, that heuristic, which is a change of rate of tangent, change of rate of n, and you have this usually standard expression for kappa and tau, which are the so-called extrinsic formula expressions. So if you want to estimate from data curvature and torsion, you should not use that. Because you know that when you have discrete data, it becomes very unstable, and when you have noise, it's really a nightmare. So I assume now that we can do that. We can have correct representation for kappa and tau, and more precisely that we can compute efficiently the Frenet Serret path, and that we can get the TNB from the data. And what's nice is, of course, if I just want to do progression analysis, so I know that if I can do this perfect analysis, that means that I have exactly the same Frenet path. Now I will go to a registration problem and to elastic shape analysis. And okay, I think that now in when you do FDA or when you do okay, all this kind of stuff about shape analysis, you have to compare with elastic shape analysis on the standard square root velocity transform introduced by Srivastava, because it provides a very interesting way of aligning curve, very effective, and it has so many success. So our idea was really how can we interpret, or how can we understand the meaning of this SRVT, but for this simple object, which are these 3D curves. So, okay, the standard representation is just to say, okay, you normalize by the square root. And so if you use the arc-length prioritization, it just gives this simple expression. And what you do if you want to align your curves, you, okay, obviously you optimize on the, you need to find the best rotation, and you need to find the best h function just to minimize that distance. And if you write it with arc-length prioritization, it just means that you just want to minimize that. Okay. Now, what happens? So, okay, imagine that you get and you want to and you get a gamma for that. So you stretch in a way your curve. So what happens really about the global geometry of your curve? So for that, we need to compute the corresponding Frenet Serret frames. So, okay, so I have this Frenet path, Q1, and I want to align in a way to Q0, okay? So what I compute, I need to compute Q1 of gamma, and then I will optimize on the gamma. And what happens is that when I look at what I get by doing this stretching, this stretched K tilde, Q tilde, sorry, is solution of a new Frenet Serret ODE, of course. And what's interesting is that you can define, you can find the corresponding generalized curvature. And the generalized curvature is the following. It just, okay, what you had at the beginning, so theta, the generalized curvature is stretched, but multiplied by gamma prime. And this is your transformation. Okay, and what's nice is that what we do is that we define a group action, in fact. And when we do the stretching, we can now compute exactly the change in the geometry and define a group action of the group of non-decreasing diffeomorphism that act in the following way. So gamma act on theta by this way by just applying this transformation, and it's a group action. Okay, and this is what we do, in fact. Okay, and then we can just generalize or rephrase the standard SRVF by saying, okay, now I don't want not only to use the first order information, just not the tangent, but the global frame. I want all the degrees of the geometry, because maybe I could be interested in that. So the idea is just to the idealization, we take any distance between Q0 and Q1, gamma S, and we use the same square root as a re-rating. And this is how we could, we expect to be able to perform interesting and maybe to open a new way of aligning curve by maybe varying the distance. And so what you can use is, of course, the Frobenius distance, or you can use also the geodesic distance between two. But okay. And then with what we do, we just extend and we apply exactly the same idea. So now if we want to do the SRVF alignment, but not with the SRVF, but with Frenet Serret, so we just minimize in H and in O and this quantity. Okay. Also, I think I forget. Oh no, it's okay. And what's nice is that if you use the Frobenius distance between pointwise Frenet Serret, okay, it's just equivalent. If you want to minimize that, it's equivalent, finally, to maximize the scalar product between Q0 and Q1. And you see really that we generalize, because with the standard SRVF, you just maximize the inner product between T0 and T1. But here it's on the whole direction at the same time. And maybe also what was not obvious to us at the beginning, that if you want to align these curves by using this geometric information by this way and by SRVF, it's not the same, it's not equivalent to align the curvature, because you could say, okay, instead of aligning directly the tangent or the tangent and the normal, I would just want to align curvature. So I compute the curvature for x0, I compute the curvature for x1, and that I want to do to align. So it will not give you at all the same alignment, the same information. Now, how can we deal with this pairwise alignment problem? So it's relatively standard. So first we compute the K0 and K1. We rescale in order to have the same length. And then what we do, we first need to find the best rotation for Q1 just to align on K0. So for that, okay, we can minimize in O this problem, or the discrete version if we have only discrete data. And then we repeat until convergence. So okay, the best stretching and then the best rotation. Okay, and obviously the tricky part is the computation of gamma, and that can be done by dynamic programming. So okay, it's also relatively standard, I think. But the idea is just to discretize your two grids, okay, with n0 and n1 points. And then you have to do two approximations. So you split, you need to approximate quadrature formula for that part. And then we use only for gamma piecewise linear approximation of the function. Meaning that if xk is the value of gamma at the point sk, so we have this following recurrence equation. And we replace this integral here by this trapezoidal rule, so which is really simple to implement. And we solve that. Okay, you can solve that relatively efficiently. So what we found very important in the use of this dynamic programming algorithm is that you cannot have the same grid size for n0 and for n1. And what you have to do is you need to have n1, the discretization for the curves that you want to align, to be much bigger, twice, than the initial one. Because sometimes your gamma can be very flat. So, but you cannot have it because you must have a diffeomorphism. So you need to allow for very small changes in the curve. And for that, in order to increase in a way artificially, so what you have to do is to do some kind of linear interpolation. So what we have done in order to increase the points, we have done linear interpolation in the Lie algebra. So between each point that we have for Q1, we do I think it has been presented before. Just we use this geodesic interpolation, and it's quite okay. And for the optimal rotation, so that's here there is a big manifold optimization part. So you just need to minimize that. So in the case of the Proteus distance, it's well known, and you just have to compute the polar part of the weight and mean. And if you use the geodesic distance on the rotation space, then you have a very efficient gradient descent algorithm to get the optimum. Okay, a small example. So our problem was just to check that we are really able to estimate correctly stretching from discrete data. So what we have done is that, we have a theta 0 here, which is our reference, and we compute Q0, the Frenet path, and we compute theta 1, which is the action of W star on theta 0, and we compute the corresponding Q1, which is like that. And now what we want to estimate the inverse, which will be our gamma star. And what you want to be sure is that our gamma star, despite our approximations in the algorithm before, is still a good provide a good estimator. So we have two ways of computing it, either by the Frenet Serret, either by the square root velocity transform. And so the geometry is relatively simple. It's not too hard. So curvature is like that, and the torsion is linear, and we have taken this expression for W. And so this is our two curves, so Q0 and Q1. And here you see the corresponding stretching function gamma. And here you should have two curves. The one computed by square root velocity transform, and the other one by the Frenet Serret. So what happened here in that case? It's pretty similar because you have no noise, and also you have no rotation, no initial rotation. So you just compute the gamma. And in that case, information is enough. In two cases, it's pretty okay. But now in that case, we just have a small rotation. So for doing the alignment, you need to find the rotation and the stretching. And in that case, the difference is teeny. But what happened is that so magenta is the square root velocity case. Yes, is a square root velocity, and the SRVF is a magenta. And what happened is that the red. So when you use the Frenet Serret, because of the way that you use rotation metrics, you estimate more efficiently the initial rotation. And then you can estimate more efficiently the gamma. And what was more interesting for us was in the case of when you have a noisy Frenet path. And noisy is, you observe, there is a typo here. You observe QE, but it is multiplied by UI, which is a random matrix Fisher distribution, a random perturbation, random rate rotation. And what happened is that the Frenet Serret, by using all this information, can give a somehow reasonable estimate of the alignment, while the SRVF, by using only the tangent information, gets stuck quite fast. So as I told you, there is a lot of perspective on this work. So the first is to get reliable estimate of the Frenet Serret path. And it was really a big part for us. And what we have done, so we are able to do this, but you can do it by, okay, so we submitted a paper, we are about to submit a paper, sorry, about the estimation of curvature and the Frenet path. And what we have done for estimate properly Q from noisy data and discrete data is we use the fact that the trajectory is a solution of an ordinary differential equation in SOP. And with that, you can control much more efficiently the noise that you have usually by standard Euclidean non-parametric estimates. And the other thing is also that we want to do multiple alignments. So in order to do that, you need to compute some kind of reference mean of the curvature, and that we speak about that in this other paper. What we found also interesting was this Frenet Serret framework is very useful in 3D. But what is power is really to be able to deal with any curve. I mean, in any dimension, because you can have expression for the curvature for a 4D curve or a 10D curve. It exists, but nobody can do it, and it's very difficult, and it uses higher order. And with this kind of framework, we have the feeling that we can deal with data in very high dimensional space just by keeping it the representation quite small. So we think that it's probably interesting to try to work around this Frenet Serret framework. And finally, the other question is about, maybe it's interesting to start having some correct reflection about what kind of distance you should take for distance between the two Frenet paths, and to interpret that correctly as a deformation or something like that. Okay, thank you.
So when you some comments on the question on the when you mean in high dimension that you still work with your 3 parameters, or you if I understand well what you are doing, you are making locally this stellar expansion and then you normalize
exactly
some Gram-Schmidt things to make the thing orthogonal. So when you say high dimensional, that means you will expand. Say you are in RD, you will expand up to D. And then you will make a Gram-Schmidt on the system of derivative locally, or you will use only the three first.
So what we do in 3D is that we compute the derivative and we do Gram-Schmidt, and then in the procedures that we have developed in this paper, then we do a smoothing of this rough estimate, and that it corrects a lot of things. But if you want to do it in 5D, then straightforward or naive preprocessing would be to say, okay, I estimate that. One good thing, maybe to say, is that an interesting property of Frenet Serret is, in 5D, so you should have 5 curvature, five functions. But if your curvature of 4 on 5 dimensions are null, vanishes, that means that you stay in a 3D space. Yeah. And so that's great.
Okay. I understand. Is that you embed in a high dimensional space, but you assume that the curve are living in a small dimensional.
Exactly.
In a smaller dimensional.
Exactly.
We talk about the influence of the distance between Q0 and Q1. Which distance do you use? What is exactly the influence?
Okay, so I can elaborate a bit on that. So what we have done was, so we have these two curves in SOP, and what we do this pointwise comparison. And for the pointwise comparison, we have used Frobenius or the geodesic distance, and the geodesic distance is better, of course. But then the next question is, okay, we use this pointwise comparison, but maybe there is a much more interesting things to do, not maybe pointwise, but maybe to define, so is there some kind of geometry on the space of curves in SOP that should be much more relevant for doing some. I do not know enough things about curves in SOP, but it was my intuition that we could do things like that.
You said that the problems become increasingly difficult once you have more noise in the data, right? Have you tried different types of noises or some distributions you assumed in order to generate the toy data you use?
So what we have done, so first, we tried this the setting that you have this nice data and you just have this kind of random rotations, which is okay, nice, no problem. Okay, okay, and if you increase, then it gets worse, of course. But we have done also another thing that you take real Euclidean data and you do the pre-processing, the complete. So you do all the non-parametric stuff. So, for instance, you do local polynomial estimation. So you got noisy estimation of your. And you do not know the law, even with the Gaussian noise and then you do that, and okay, so you just have to increase a bit, and you have a lot of problem. And of course, what happens that at the boundaries, it's really messy.
And you have not tried some type of uncertainty quantification or Bayesian stuff on this? I mean, not to get a unique sort of. I mean, this is of course. Nothing specific, but maybe some distribution of curves, something like that.
So yeah, so typically it was one of the next steps to imagine that you could say, okay, Frenet Serret is completely deterministic. So if I put some noise in my Frenet Serret, maybe I can do filtering and and all the problems are.
You have thought about it?
Yeah.
Okay.
I just need to program.
Okay. Thank you.
So thank you very much.
Thanks.